Welcome to Lesson 7. Here we're going to work through some AP style related rates problems. So to get us started, let's take a look at what will probably appear to be a very simple discovery problem, and it is supposed to be, so do not overthink it. Alright, very simple situation here. You have two variables and you know the value of one of them. What would you need in order to determine the value of the other one? Well, you need a relationship between the two of them. So for example, if you could also ascertain that y is equal to 2x, then if you know that x is equal to 7, you know that y is equal to 14. In other words, the crux of this situation is that you're able to write a relationship between the two variables. And this is the exact same situation that we must handle when we're dealing with a related rates problem. Obviously, there are a few more things that we need to consider and steps that we need to take, but ultimately we have some rates that we know, and there is one rate that we're trying to find. And so we need to write a relationship between the rates that we know and the rates that we're trying to find. And it all starts with a single equation where we're writing a relationship between the variables whose rates we eventually want to write a relationship between. And then, of course, through implicit differentiation, we can then take that equation and write an equation which represents a relationship between the rates that we know and the rates that we're trying to find. And thereby we can solve for the rate that we're trying to determine. So I'm going to post the strategy that we've worked through many times over for solving related rates problems, just to make sure that we're on the same page when we go through and start tackling some of these more nuanced AP style related rates problems. Okay, so here are the 6 steps that we've worked through for solving related rates problems, and the basic principles of the strategy we just discussed, which are we need to create a mathematical model which relates the rates of change which we know and the ones we're trying to find. In order to get to that step, where in step 4 we're differentiating an equation in order to get this relationship of rates, we have to spend a lot of time understanding the problem, developing a mathematical model, and drawing a model picture of the situation, so that we can then accurately write an equation that involves the variables that have the variables for the rate of change that we seek and the rate of change that we know. So that we then differentiate that equation, we'll have a relationship between the rates of change that we know and the rates of change that we're looking to find. And then, and only then, can we then substitute in some values of rates of change that we know, potentially some other variables whose values we know at an instant in time, to find the rate of change that we're trying to ascertain. And of course, don't forget to interpret your solution with correct units in order to answer the question that is posed. Alright, so let's go ahead and take a look at a couple of problems. Okay, here we go. A street light is at the top of a 16-foot tall pole. A woman who is 5.5 feet tall walks away from the pole in a straight path at a constant speed of 4 feet per second. We have two questions. The first is, at what rate is the length of her shadow changing when she is 25 feet away from the pole? And the second question, how fast is the tip of her shadow moving when she is 25 feet away from the pole? So go through those steps, answer both questions on your own first. None of this is really new, and so you can undoubtedly carry through and find the correct solution on your own, and then go ahead and take a look at the solution to make sure that your answer includes all the necessary components. Alright, since I'm going to need a visual for both parts A and B, I've just drawn that first. Here's my 16-foot lamp post with the light at the top. Here's my 5.5 foot tall woman. I've illustrated that she's walking away from the lamp post. And here we can see her shadow. So her shadow is going to be length x. It's the part of the light she's blocking out. and then length y is going to be her distance away from the lamppost. And of course, we also know that she's walking away from the lamppost at a constant speed of 4 feet per second, so we know that dy dt is 4 feet per second. All right, let's go ahead and get into part A. Okay, so first off, I know that I'm looking for the rate at which the length of the shadow is changing. Now the length of the shadow is x, so I'm looking for dx dt, and the rate of change that I know is dy dt. I know that the distance that the woman is walking away from the pole is increasing at a rate of 4 feet per second. So now I need a relationship between y and x so that I can differentiate it implicitly with respect to time to find a relationship between their rates of change, and then I can solve for the rate of change that I seek. So here's where I'm going to need to utilize similar triangles. So notice here that I have a large triangle, and this large triangle has a vertical side length of 16 and a horizontal side length of y plus x. Okay. Inscribed inside this triangle is a smaller triangle with a vertical side length of 5.5 and a horizontal side length of x. Now what I know about similar triangles is that their corresponding side lengths have the same ratio, which means the ratio between this side length and this side length is going to be the same as the ratio between this side length and this side length. So since they're going to be equal, those ratios are going to be equal, I can write an equation using that piece of information. Okay, so based on that, I have an equation now. Again, this represents this side length, 16 is the vertical side length of my larger triangle, and that ratio between those two side lengths has to be the same as the ratio between the corresponding side lengths of the other similar triangle. So the horizontal side length of that smaller triangle is x, and the vertical side length of that triangle is 5.5. So I'm able to write this equation here. Now I'd like to actually simplify this a little bit. I don't like to deal with fractions when I differentiate, so if I just multiplied by 5.5 and multiplied here by 16, and then what I could do is I'll have 5.5x plus 5.5y equals 16x, and I can collect all the x's on one side. At this point, I'm good to go ahead and differentiate if I'd like, but if I wanted to simplify this even more, I could divide on both sides by 5.5 so that I would have a little bit less work to do after I differentiate. And you certainly can do that, but I might just go ahead and differentiate now with respect to t on both sides of my equation. Going ahead and differentiating on both sides with respect to t, I'm able to write an equation that relates the rates, the rate that I know, dy dt, and the rate that I seek, dx dt. So now substituting in 4 for dy dt, I can solve for the desired rate, dx dt. And therefore, I am able to find that dx dt is 2.1 feet per second, approximately. So you'd want to go ahead and write out your answer there, stating that the rate at which the length of her shadow is changing at that particular moment is 2.1 feet per second, approximately. Now, it's important to notice that you didn't use this piece of information that told you that the instant in which you're looking at is when y is equal to 25 feet. And the reason you didn't need that is when you differentiated, you found that dy dt and dx dt were in your equation, but x and y were not. And so you had no need for the y value that was given. So don't feel as though you need to use every piece of information given in a problem in your answer. This is something that shows up a lot on AP questions where they want to test and make sure that you're not just taking all of the information you're given and throwing it and force feeding it into some equation that you're coming up with. So you need to make sure that you're comfortable with the strategy and the process so that you're able to trust yourself when you're not using what's called extraneous information. All right, let's go ahead and work on part B now. All right, part B is the trickier part of this question. And the reason that it's trickier is if it were asked without having first asked part A, you might confuse the two. So there's a big difference, and we'll see that in a second, between the change of the length of the shadow, how the length x is changing, and how fast the tip of the shadow is moving. So let's illustrate this difference. Let's first notice that the tip of the shadow is going to be right here. And in order to ascertain the rate at which the tip of your shadow is changing, we need to think about the different things that make up the rate at which it's moving. So let's consider this tip of the shadow here. And think about in our diagram the pieces whose change or whose rate of change is going to affect the rate at which the tip of the shadow moves. At first, you might say to yourself, well, it's just going to be the rate at which the shadow itself is changing. But you'd be incorrect, and here's why. Because while the shadow itself is changing, so too is the distance that you're walking away from the light source. So y is increasing, and x is increasing, as we saw. That means that the tip of your shadow is not just changing because of the shadow itself, but also because of the fact that you are walking away from the light source. In other words, the tip of your shadow is changing at the same rate as this entire horizontal length. Not just the length of x or the length of y, but in fact the total length, which is y plus x. So the derivative, or the rate of change that we're actually trying to find, is the derivative of this entire side length, which we can call, as we just talked about, x plus y, or y plus x. So the derivative that we seek, the rate of change that we seek, is this. The derivative, of course, with respect to time, of the side length x plus y. Now this looks a little interesting. Notice that we're taking the derivative with respect to time of something plus something else. But this is something we've done many times before. Taking the derivative of two functions that are being added together means that we can take the derivative of each function separately and then add them. Since each of these values, x and y, depends on time, and we're differentiating with respect to time, we can rewrite this. What we seek is simply the derivative of x with respect to time plus the derivative of y with respect to time. This is the derivative that we seek. This here will give me the value of the rate at which the tip of the shadow is changing. Notice that it builds in both components that we discussed. The tip of the shadow is going to change not just because the shadow itself is changing, but also because you are walking away from the light. So both the rates at which y is changing and the rate at which x is changing are going to influence the rate of change of the tip of your shadow. To see this in real life, I encourage you to find a light source and stand in a position where you can see your shadow. And if you walk away from the light source, you'll notice you can actually feel the two components which are changing or affecting the rate at which the tip of your shadow moves. You'll feel yourself walking. That is one component. In other words, that's the rate at which y is changing. And you'll also notice that the shadow itself is going to be changing. And so you can see the two components affecting the tip of your shadow and the rate at which it's moving. So now that we have this down, we can actually note that we've done all of the hard work. We need to find dx dt and dy dt. Well, we know dy dt, it's 4, it's never changing. And we know dx dt at this particular moment as well, 2.1 feet per second. That's what we found in part A. So we don't need to construct any new equation. We don't need to differentiate implicitly. In fact, we already did that differentiation piece here. And so all we need is the value of dx dt and dy dt at this particular moment, which we already have, 4 and 2.1. So adding those together, I get approximately, I should put approximately there, approximately, since this is an approximation, 6.1 feet per second. So writing out your answer, the tip of her shadow at this particular instant is moving at a rate of 6.1 feet per second, approximately, or at a rate of approximately 6.1 feet per second. This is where a simple understanding of the situation is going to go a long way. So make sure that you take your time with that, and don't think that you're ever spending too much time with the first couple of steps. Notice that that was really the only step that we needed to make here. And so as long as you take your time and you trust your intuition and the sense and logic behind your reasoning, you will be just fine. All right, let's go ahead and take a look at one more AP style related rates problem. Okay, so here we have a situation. We're told that the volume V of a cone is increasing at a rate of 4 pi cubic inches per second. At the instant when the radius of the cone is 2 inches, its volume is 8 pi cubic inches, and the radius is increasing at 1/3 of an inch per second. In this particular question, which is actually in your textbook, it is number 70 in the chapter 5 review section. They tell you the equation for the volume of a cone that is given to you. And even though they give that to you, there's one equation that you need to recall, but hopefully you have memorized. So you can go ahead and take a look at that, or you can Google the volume of a cone and use that equation. Go ahead and work through A, B, and C. My one recommendation here is to spend some time creating your diagram and making sure that it is totally accurate before you go into each question. All right, so here's my diagram. I have a cone, I have the height, the variable h, radius, the variable r. And here's the equation for the volume of a cone, which is 1/3 pi, or pi over 3, r squared h. And question A says, at the instant when the radius of the cone is 2 inches, what is the rate of change, I forgot to put that word in, change, the rate of change of the area of the base. All right, a couple of things to note here. We're looking to find the rate of change of the area of the base. So the key to this part of the question is determining, first off, what's the area of the base, and what is the rate of change that we know that is going to allow us to write an equation, or to instruct us how to write an equation that will create a relationship between the rates that we know and the rate that we seek. All right, so to save a little space, I've written down the information that I'm given here, and I'm just going to refer back to it for each part. Of course, I know the rate of the radius with respect to time, that's 1/3 inch per second. And I also know the rate of change of the volume with respect to time, which is 4 pi cubic inches per second. And I'm also told that when the radius is 2 inches, the volume is 8 pi inches cubed. So that's all the information I know. For part A, I want to find the rate of change of the area of the base. So I'm looking for dA dt. And A here represents the area of the base. Now, what is the rate of change that I know, which I can then use to relate to the area? So there's a couple ways to think about this. The first is just to immediately say to yourself, well, what is the area of the base? Well, remember that the area of the base is the area of this circle here, and the area of a circle is pi r squared. So it'd be helpful to go ahead and write down that the area of the base is going to be pi r squared. So with this in mind, we know that we can use this equation here, and so we're going to be using the fact that the rate of the radius is 1/3 of an inch per second, and that'll allow us to relate dA dt and dr dt. So we'll use this equation here, and we'll differentiate with respect to t. Okay, so here is my equation. The area of the base is equal to pi r squared. So this would be, step 3 if you're following along. I already have my diagram and I know what the rate that I seek. And then here I'm going to differentiate implicitly with respect to t, which gives me that dA dt is equal to, I pull out the pi because that's a constant, the derivative of r squared with respect to t is going to be 2r dr dt. And now I want to evaluate this when the radius of the cone is 2 inches. Alright, so evaluating when r is equal to 2, I get that dA dt is 2 times pi times the radius, which is 2, times the rate of change of the radius, which is constantly 1/3, which gives me 4/3 pi. And my units here, this is area, so it's measured in square units, and the units here are inches, so it'll be inches squared per second. So that is the answer to part A. All right, let's take a look at part B. All right, for part B, I am looking at the same instant when the radius of the cone is 2 inches, and here I'm looking for the rate of change of the height. So here the rate that I seek is going to be dH dt. And if I take a look at the other rates of change that I know, notice here that the volume of a cone is an equation that relates volume, radius, and height. And here I want the derivative with height with respect to t. So there are actually a couple things that I can relate here. The first is that I can relate the height and the radius to the volume. And so in doing that, I can actually write an equation that relates 3 variables together. And since I know dr dt and I know the radius, I will be able to solve for dH dt when I plug in the constant rate of change of the volume. All right, so to save a little bit of space, I'm just leaving my equation that relates my variables up here. Now, you'll notice there are a couple of options. I can go ahead and differentiate with respect to t. And the reason I can do that without making r or h, without turning this into an equation in one variable, is because I already know dr dt. So when I differentiate here, I'm going to end up with an dr dt, and since I know that value, I will be just fine. But you're perfectly fine as well going through and trying to find a relationship between r and h. It's just that in this case, that is not going to be the easier route. So we're going to differentiate here with respect to t. Notice that r and h are both functions of t, so I'll be using the product rule here after I factor out the pi over 3. All right, so going through, when the radius is equal to 2, I'm able to input the value of dV dt, which is 4 pi, the value of r, and dr dt, which is 2 and 1/3. Now, the value of the height, you have to go find. And the reason that you can go find it is they give you a little bit of information. The radius is 2, then the volume is 8 pi. And since you have that equation with v, r, and h, you can input values for v and r and solve for h. So you have the equation 8 pi equals pi over 3, 2 squared h, and solving for h, you get h is equal to 6. So at this particular instant, the height is equal to 6. Plus the radius squared, which is 2 squared, times dH dt, which is what we're seeking. Solving for dH dt, you will get 1, and the rate is in terms of inches per second, since the height is one-dimensional. So dH dt is 1 inch per second. Okay, so part C is certainly the most complex of the questions, and also probably the simplest once you understand the relationship that you can use. Here we seek the instantaneous rate of change of the area of the base with respect to the height. So this is an important distinction. The derivative of the area with respect to the time, which we found, area is measured in inches squared, and time is measured in seconds. So that's why we ended up with 4/3 pi inches squared per second. Here we have the derivative of the area with respect to height. So in other words, we're going to end up with some number of inches squared per inch, and that per inch refers to per inch that the height changes. Now, what we want to take advantage of are the derivatives we already know. We already know the derivative of area with respect to time. Let me go ahead and just write that out here. We know the derivative of area with respect to time. And we also know the derivative of the height, because that's the other thing that is involved here, and we just found that the derivative of height with respect to time, we found that to be 1. Now, notice that there are a couple things that these have in common. They're both in respect to time, and we ultimately want the derivative of area with respect to height. So if you think about this particular rate of change, the units are inches squared per second, and this rate of change is inches in height per second. What we seek is the derivative of area, or inches squared, per the derivative with respect to the height, or inches squared per inch. So we need this dH to be in our denominator. And notice that both of these derivatives are with respect to time. So if I were to think of these as just fractions, and I were to take the reciprocal of dH dt, it would be dt dH. Multiplying those two rates of change would then allow me to cancel out the time component and to simply have the rate of change of the area with respect to the height. All right, so you see here dA dt times dt dH. That is going to allow me to cancel out the time component, because notice the units here are inches squared per second, and the units here are now, because I've taken the reciprocal, seconds per inch. So when I multiply those two units of measure together, the time components will cancel, because there'll be one in the denominator, one in the numerator. So I'll end up with inches squared per inch, which is going to be the units of my rate of change. Inches squared per inch. And this corresponds to the rate of change that I sought, which was the rate of change of the area, inches squared, per the change in the height, or per inch. And you think of this per inch as per inch change in the height of the cone. So this is a relationship that you can take advantage of anytime that you seek some unique derivative. Check to see if you have a couple of derivatives already, a couple of rates of change that you can work with that will eventually give you the rate of change that you seek. And this works for any set of variables that you have. All right, so with that being said, go ahead and move on to 5.07 and take your time with these. These can be challenging, but the result will be well worth it.